Take a breath. The carbon dioxide you exhaled could end up in an oak tree, a limestone cliff, or the deepest ocean trenches. Carbon is the chemical scaffolding of all known life. It forms our DNA, our proteins, and the sugars that provide our energy. Earth is a closed system. Almost zero carbon enters, and none escapes. We operate on a finite ledger. The location of this supply dictates habitability. Too much carbon in the atmosphere, the globe turns into a furnace. Too much underground, it becomes a frozen wasteland. To survive, the planet relies on a dual-speed engine to cycle this carbon and maintain equilibrium. The first part of this engine operates at the speed of life, running on a loop of days to years. Through photosynthesis, plants pull carbon dioxide straight out of the air, using it to build sugars and grow. Animals eat those plants, use the carbon for energy, and breathe it right back out as carbon dioxide. When living things die, bacteria and fungi break down their remains, venting the leftover carbon back into the sky. This chart plots atmospheric carbon levels over a single 12-month period. The sharp plunge you see here happens every spring, when millions of plants begin growing at once. The drop is so massive, it looks like Earth is taking a giant breath. The fast cycle is a reactive loop that balances exactly what it consumes over short periods. The second tempo operates on a geological timescale, taking roughly 100 to 200 million years to complete a single loop. Airborne carbon mixes with rain to form a mild acid. This rainfall dissolves minerals out of surface rocks and eventually washes them down into the sea. In the ocean, marine organisms use dissolved carbon to build shells, which sink and compress into seafloor limestone. Over millions of years, trapped organic matter under intense pressure turns into coal, oil, and natural gas. This buried carbon only returns to the atmosphere naturally when tectonic plates collide and volcanic eruptions vented back into the sky. By locking away massive quantities of carbon over eons, the slow cycle acts as the planet's shock absorber against runaway greenhouse heating. Human extraction of fossil fuels breaks this natural rhythm. We are taking carbon stored by the slow cycle over hundreds of millions of years and injecting it directly into the fast cycle. Combustion releases this carbon in a fraction of a human lifespan, a rate hundreds of times faster than it took to bury it. The natural cycle simply cannot keep up. This rapid transfer overwhelms the planet's natural sinks. The oceans are currently absorbing about 55% of this extra carbon. Forcing that much carbon into the hydrosphere triggers severe ocean acidification, breaking down the marine life that helps regulate the cycle. The remaining 45% stays airborne. It functions as a greenhouse gas, trapping the sun's infrared heat and warming the globe. The climate crisis is a timing error. We are overloading a system built for a daily cadence with fuel meant to be processed over eons. This warming triggers feedback loops. Rising temperatures thaw frozen permafrost, unleashing ancient carbon from plant matter that never fully decayed, which drives temperatures even higher. Deforestation delivers a double blow. We remove the green plants acting as fast-cycle carbon vacuums, while simultaneously releasing their stored carbon when they rot or burn. The carbon cycle will easily survive this interference and find a new equilibrium, but the resulting climate will not remain hospitable for us. Restoring the balance requires two actions. We must protect our fast cycle sinks, and we must leave the slow cycle carbon securely underground. Solving climate change requires humanity to respect the planet's ancient built-in speed limits.